Our research group is the Ultrasonics and Non-Destructive Testing research group. One of the big areas that we work on is non-destructive testing, and in that there are things like characterizing materials, finding defects, so imaging structures. We're also interested in other uses of ultrasound, so one of our big areas is using ultrasound to manipulate objects. So when a wave passes by an object, there's a force exerted on that object. So we're trying to use that force to move cells for potential tissue engineering applications, and also to move small particles for materials manufacturing applications. One of the key things that ultrasound enables you to position the cells with less reliance on a scaffold. So the scaffold is some physical construction that most tissue engineering is based on, and that then has to be implanted in the body with obvious negative consequences. So if we can remove the need for this tissue or use less tissue, it could create much better tissue and ultimately much better organs.
A big part of our research is about ultrasonic phased arrays, so using arrays, just as you have for fetal inspection or kidney treatment, things like that, and using those for imaging. There are commercial bits of kit that are small, but they're essentially implementing the techniques we developed on our larger lab-based equipment. What we also have is an exciting new set of technology developing where we essentially have a very light piece of equipment that we use to go and inspect a structure, moving it over like a magic wand to tell you about what's going on inside. Which is leading to a spin-out at the moment. So an example of sort of where research goes, one route for that research to get out of the lab and into the real world.
The infrastructure in the UK is progressively getting older. The most cost-effective solution is to try and get the plant that you've currently got to last longer. And the only way you can do that safely is to quality assure the current plant. And that gets more and more demanding as each year goes by. And so one of our big areas of collaboration is with people working in the power generation and nuclear power generation sectors to try and characterize exactly what's going on in their structures. So that might be finding really, really small defects, or there might be some defects that are known to exist. But if we can say a bit more about exactly their shape and their impact on the structural integrity, that will allow them to make better predictions as to what's going to happen in the future to that plant. And there's a whole load of that sort of plant that's only really being kept going because of such testing. All this talk of moving things around with ultrasound, so applying a force at a distance, might remind you of things you've seen on TV, for example, Doctor Who's sonic screwdriver or a tractor beam in Star Trek, and there is a kind of a link. But actually, it turns out that there's some physics behind it, so you can apply forces at a distance using ultrasound. And so the work we've been doing where we're moving cells, moving fibres, is exactly a form of, in a way, a microscopic version of the Doctor Who sonic screwdriver or a tractor beam. We're not yet at a level where we can move asteroids and spaceships, but we can move cells and small particles with ultrasound. So what excites me about my research? Well, for some strange reason, I've always been interested in waves from quite a young age, and so I now have the privilege of working on ultrasonic waves, which you can't hear. On a fairly regular basis, we make measurements or understand phenomena that no one's ever seen before, so that's incredibly exciting.
The other really exciting things are when you go and visit industrial partners that you've been working with for 5-6 years, and you see work that was in your lab being used in a factory. That gives you a real buzz, a real sense of achieving something.